Hello, in this problem we're given a 3 by 3 matrix A, and the first part asks us to find all the eigenvalues of A together with their algebraic multiplicities. To do that, we need the characteristic polynomial of A. We write it like this. Determinant of A minus lambda times the identity equals 0. So from the matrix A, we subtract lambda times the identity. Here it is written out. Determinant of the matrix with first row 4 minus lambda 0, 0. Second row 4, 10 minus lambda 1. Third row 0, 0, 4 minus lambda. Now how do I take this determinant? I expand along the first row. I take the top left entry, 4 minus lambda, and I cover up the first row and the first column. What remains is a 2 by 2 block. So I write the determinant of that leftover matrix, 10 minus lambda 1, 0, 4 minus lambda. The definition is recursive in that sense. Now let's recall how to take the determinant of a 2 by 2 matrix. Let's remember the rule for a 2 by 2 determinant. For the matrix A, B, C, D, the determinant is A times D minus B times C. So what do we get here? 10 minus lambda times 4 minus lambda minus 1 times 0, which is just 0. So the whole thing becomes 4 minus lambda times 10 minus lambda times 4 minus lambda. And if we tidy that up, it is 4 minus lambda squared times 10 minus lambda. Now up above, when I computed the determinant, why did I not use the second and third entries of the first row? Because those entries are 0, so they would contribute nothing and would not change the determinants at all. They simply drop out. Now we can find the eigenvalues. How? They are the values that make this characteristic polynomial equal to 0. So lambda equals 4 and lambda equals 10 are the eigenvalues. Now look at the powers. 4 minus lambda appears squared and 10 minus lambda appears to the first power. What does that tell us? These exponents give the algebraic multiplicities of the eigenvalues. Since the factor 4 minus lambda is squared, the eigenvalue lambda equals 4 has algebraic multiplicity 2. Let's write it down. Lambda equals 4 with multiplicity 2. And the other eigenvalue, lambda equals 10, has multiplicity 1. Now part 2 asks for the eigenvectors corresponding to these eigenvalues. So we're really finding a basis for each eigenspace. How do we do that? Let's start with the eigenvalue 4. To build a basis for the eigenspace of lambda equals 4, we look at a null space. The null space of what? The null space of A minus 4 times the identity. So let's compute that. From A, I subtract 4. Subtracting 4 times the identity just means subtracting 4 from the diagonal entries. So A minus 4i is the matrix with rows 0, 0, 0, then 4, 6, 1, then 0, 0, 0. Now how do I find the null space of this? I look for vectors v such that A minus 4i times v equals 0. So let's take a general vector v with coordinates x, y, z. I write A minus 4i here, rows 0, 0, 0, then 4, 6, 1, then 0, 0, 0, multiplied by the column x, y, z, and this equals the 0 vector. Now multiply the first row by the vector, 0 plus 0 plus 0 equals 0. That gives us no information. But from the second row, we get 4x plus 6y plus z equals 0. Now, from that equation, I can solve for z. Z equals minus 4x minus 6y. So my vector xyz becomes xy minus 4x minus 6y. Now I factor out x, which gives 1, 0 minus 4. And I factor out y, which gives 0, 1 minus 6. So the vector is x times 1, 0, minus 4, plus y times 0, 1, minus 6. These two vectors form a basis for the eigenspace corresponding to the eigenvalue lambda equals 4. Let's write them down. v1 equals 1, 0, minus 4. And v2 equals 0, 1, minus 6. Now we're going to do the same process for the eigenvalue 10. Null of A minus 10 times the identity. That's the space we need. So from A, I subtract 10 times the identity matrix, which means I subtract 10 from each diagonal entry. Same idea as before. The first row, 4 minus 10 gives minus 6, then 0 and 0. Second row starts with 4, and we keep subtracting 10 along the diagonal. Second row, 4, 10 minus 10 is 0, then 1. Third row, 0, 0, and 4 minus 10 is minus 6. Now we look at the null space of this matrix. So this matrix is A minus 10 times the identity, and to find its null space, I'll use the augmented matrix method. I write the matrix exactly as it is, minus 6, 0, 0 in the first row, 4, 0, 1 in the second, 0, 0, minus 6 in the third, and on the right side of the bar, I put 0, 0, 0. Now let's row reduce this. I'll multiply the first row by minus 1 over 6, so that the first row becomes 1, 0, 0, and the right side stays 0. I can do the same thing with the third row. The third row also gets multiplied by minus 1 over 6, which turns it into 0, 0, 1. The second row I leave untouched, 4, 0, 1. So now we have 1, 0, 0 on top, 4, 0, 1 in the middle, and 0, 0, 1 at the bottom with zeros on the right. Now what do we see? I can take the first row, multiply it by minus 4, so minus 4 times the first row, and add it to the second row. That kills the 4. So we get 1, 0, 0, then 0, 0, 1, then 0, 0, 1. The right side is still 0, 0, 0. It stays all zeros. Now the second row and the third row are identical, so subtracting one from the other eliminates a row entirely. What I'm left with is this: 1, 0, 0 in the first row, 0, 0, 1 in the second, and 0, 0, 0 in the third, with zeros again on the right. Now what does this tell me? The first row says x equals 0, the second row says z equals 0, and y can be anything at all. It's a free variable. Remember, the first column corresponds to the variable x, the second column corresponds to the variable y, and the third column corresponds to the variable z. So x and z both have to be 0. For a vector in this null space, y is completely free. Any value works, so whatever we put in for y doesn't matter. We just write y equals y. That's how we record a free variable. So the vector that spans this space has components x, y, and z, and since x and z are 0, the vector is 0, y, 0, and that's y times 0, 1, 0, so 0, 1, 0 spans it. I factor the y out front, and what's left is the vector 0, 1, 0. That single vector spans the eigenspace corresponding to the eigenvalue 10. Let's call it v3. So I write v3 equals, and v3 is 0, 1, 0. Now let's see what comes next. Let's finish writing the third eigenvector. v3 equals 0, 1, 0. With that, all of the eigendata from parts 1 and 2 is on the board, and we can move to part 3 of the question. Part 3 asks us to find an invertible matrix P such that P inverse times A times P is a diagonal matrix D. Let's clear away the scratch work from the earlier part so we have room. Here's the method. If the matrix in front of us is diagonalizable, and this one is, then we can build P and D straight from the eigenvalues and eigenvectors. So how do we know A is diagonalizable? Lambda equals 4. Let's check this eigenvalue first. From part 1, its algebraic multiplicity is 2, because it showed up twice as a root of the characteristic polynomial, 2. That's the algebraic multiplicity for lambda equals 4. And the eigenspace for lambda equals 4 came out two-dimensional, spanned by v1 and v2. So the geometric multiplicity is 2 as well, 2 equals 2. Now look at lambda equals 10. Its algebraic multiplicity is 1, and its eigenspace is spanned by a single vector, so 1 equals 1. For every eigenvalue, the geometric multiplicity matches the algebraic multiplicity. That is exactly the condition we need. So A is diagonalizable. A equals P dP inverse. That's what diagonalizable means. There exists an invertible P and a diagonal D satisfying this equation. And if you multiply on the left by P inverse and on the right by P, it rearranges into P inverse AP equals D, which is what part 3 is asking for. So what do we take for P? P equals the eigenvectors written as columns. First column 1, 0, minus 4. Second column 0, 1, minus 6. Third column, 0, 1, 0, which is v3. Now what is D? D carries the eigenvalues that correspond to those columns in the same order. The first column is 1, 0, minus 4, and the eigenvalue attached to it is 4. So 4 goes in the first diagonal entry. The second column, 0, 1, minus 6, corresponds to 4 again, and the last column, 0, 1, 0, corresponds to 10. So D is 4, 4, 10 down the diagonal, with zeros everywhere else. And with that, we've answered part 3 and part 4 at the same time, because part 4 just asked for the diagonal matrix D. As we said, D is the arrows point down to the diagonal entries. Each eigenvalue sits in the same position on the diagonal as its eigenvectors column in P. Here's the key point. The first column of P is 1, 0, minus 4, so I wrote 4 in the first diagonal slot, not 10. The order has to correspond, column by column. That's the full exam question. See you in the next one.